About any questions about last class? Okay, so what's wrong with this phase diagram? This is the point where we left last time. So any ideas? What's wrong with it?
Is it the intersection all the way to the right on this graph? How it has four.
Which one?
The intersection all the way to the right.
This,
At the
this
first,
one
at the
here?
highest point T. Exactly. It has four
That's
phases existing at
yeah,
once.
exactly. That's the only thing. And why is that wrong? Because if you look at it, we have our Gibbs phase rule, F is equal to C minus P plus 2. And this is a one component system. So C is 1. And there are 4 phases existing here. So 1 minus 4 plus 2. So that's minus 1. That doesn't make sense. So every other region, so here you have to check for everything in order to be careful. If I give a problem like this, or if you get a problem like this, you have to check for every region. There could be a problem maybe in a region. There could be problem maybe at a boundary. There could be problem at a triple point. There could be problem somewhere else. So you have to check all of them. But in this case, this is the only one where you can't have it. Now, if it was a 2-component phase diagram, then this would be possible. In a 2-component phase diagram, you could have had 4 phases coexisting at the same time. Great. So, no more questions? How do we check a boundary line? Well, we do the same thing. We go to a boundary. Good question. So we go here and we say, okay, F is equal to C minus P plus 2. How many components do we have? 1. How many phases is it? Say boundary. What does boundary mean? Boundary means coexistence between phase alpha and phase delta. So both alpha and delta exist at the same time. Therefore, minus P is minus 2, and then plus 2 is equal to 1. So 1 degree of freedom. And straight line is exactly 1 degree of freedom. So it makes sense. If you go to a region over here, what is F is equal to C minus P plus 2? This is F is equal to 1 component minus number of phases, which is 1 plus 2 degrees of freedom. And hence you have area in the phase. So that's what it is. Let me upload this file so it updates on the website. How do I do that? Okay. Export all. Okay. Any more questions?
Yeah. So do the phase lines so like whenever you like move from like solid to liquid or like a liquid to gas, temperature stays constant through that phase change process. Is that what the line, like the fact that it's like a solid line, does that factor into it at all?
One moment. I'm just trying to upload this new note and I'll get back to you. Just a moment. Sorry about trying to multitask. Save here, upload. Okay. So you're talking about this line over here, right?
Yeah.
And what's your question exactly?
Like, does the line account for, or I guess not account for, but does it like kind of like allude to that like through phase changes the temperature stays constant even though heat's being like added to the system?
Yeah, precisely. This line is a specific point of pressure and temperature, right? So what this is showing you is, that's a great point. And we will be doing examples like this later. Let's imagine this vertical line that goes down from here, okay? So you start in phase alpha and you are decreasing the pressure as at the same constant temperature. You're doing an isothermal calculation. The temperature is held constant and you're bringing alpha down to delta. So at some temperature, at some pressure, as you keep decreasing the pressure, delta is the phase that will show up. But there will be one particular pressure at which both of them will coexist. You will see in your sample. So if I make my sample, it will first look like alpha. Gradually, it will start to all will look like delta. But there will be a middle region at a particular pressure where you will have alpha plus delta coexisting together in the sample. And we will be looking at examples of this. How do they coexist? What it goes on? So in an experiment, it might actually feel like you're trying to decrease the pressure and it's not decreasing. Something's happening and both of them are existing at the same time. And then as you keep decreasing it further, it will be, it's like trying to trying to, really squeeze something really, really tight. At some point you can't do anything. It's just held, and finally it gives in. And I can think of only bad analogies, but you know what I mean. You start decreasing the pressure. You start, in this case, you're decreasing the pressure. So it's more like stretching something, stretch, stretch, stretch. And at some point you can't really stretch anymore. Something has to give in. And when that something breaks internally, then you can stretch it even more. You see what I mean? So yeah, it's at this point is a specific pressure and temperature. That's what's happening over here. Now you could have had a phase. One point I would like to make is that you could have had a phase transition in a separate setup. You might have had a phase transition where the pressure is actually changing. Here we are talking about pressure temperature phase diagrams mostly. So it's okay to think about happening at a constant pressure and a constant temperature. And what really goes on during this process, we will be looking at it quite a lot. How does the free energy curve look like? What is really the mechanics of this? We will be looking at it. Does that help or confuse you more?
Yeah, no, that helps. Thank you.
Okay, good. Okay, any more questions? If no, then let's finish our proof of Gibbs phase rule. So we are trying to prove F is equal to C minus P plus 2. Last time, we did this for C is equal to 1, right? For one component system. Now, let's do for general case, or actually sub case in a sense. No, general case where C is more than equal to 1. C can be anything. So it will be a bit more mathematical, but it will be a very, very general proof. So how do we do this? So let's count the total number of intensive variables. So let's count the total number of intensive variables. So what will it be? First of all, we have pressure, right? That's an intensive variable. We have temperature, that's another intensive variable. And when we were doing the C is equal to 1 case, that's it. Those two were the only two intensive variables. There was nothing else we could do. But now we can also vary the mole fractions of different phases. We have a C component system, we have C components, and we have P phases. Every phase can have a different varying number of mole fraction. What do I mean by that? Let me write it down. So now in addition, not component, but composition of every phase can be varied. And it's intensive because we are only changing the relative amounts. Composition of every phase can be varied. So what does it mean? Every phase has C components. And we can vary all these components at the same time. However, we have an additional constraint that sum of mole fractions must be equal to 1. So what do I mean by this? Let's say I'm looking at phase number, some phase. So we have phases I going from 1 to P, right? The number of phases we have, I can go from 1 to P. So let's look at phase number I, which is I is some value between 1 and P, and we have component number 1, we have component number 2, and like this we have component number C in this phase. Similarly, we have component number 1 in phase number I plus 1, component number 2 in phase number I plus 2, I plus 1, component number C in I plus 1, and so on and so forth. We have such, how many such compositions do we have? We have P such things, P multiplied by C, right? Every phase has C components. So we have P into C things that we could vary at the same time. However, we have a constraint that inside every phase, it should sum up to 1. inside every phase, this should all sum up to 1. So the independent number of variables, independent number of intensive variables that we have, independent number of intensive variables is P multiplied by not C, but C minus 1. Because for every phase, we have said there is a constraint. This is only using the composition. Adding pressure and temperature, we have P multiplied by C minus 1 plus 2 intensive variables that can be varied. And so this, what do I mean by intensive variables that can be varied? This is the number of degrees of freedom we could have had, but we have additional constraints that we haven't taken into account. So if this was just the case, we could have written F is equal to P multiplied by C minus 1 plus 2, which would be PC minus P plus 2. Something's really wrong, right? We were just trying to derive F is equal to C minus P plus 2, and we just ended up with F is equal to PC minus P plus 2. Something is wrong, right? We forgot about some constraints. What are the constraints that we forgot about? So P is more than 1, right? You have more than 1 phases. So this is telling us that the number of degrees of freedom is, this number PC minus P plus 2 is going to be much larger than the number C minus P plus 2. That makes sense, right? Because PC is more than P. So why do we have suddenly more degrees of freedom? Did we forget about a few constraints? What are the things that we forgot about? We forgot about equilibrium, that the system is in equilibrium. So we have to equate the chemical potential, which we totally forgot about. So we have P phases going from 1, 2, 3, dot, 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 till P. And for any given species, we will have equilibrium given by the chemical potential. That means that species number 1 in phase, and this P business is going to get a bit, okay, so P, capital P is the number of phases and small p is the pressure, and I apologize for that, and I will try to write carefully so it does not confuse you. So for phase number 1, at a particular pressure and temperature, the species 1 should have the same chemical potential as it has in phase number 2 at that pressure and temperature, same as phase number 3 at that pressure and temperature, equal to phase number capital P at that pressure and temperature. So what have we said here? We have a C component system, right? We took component number 1 and we said that at equilibrium, the chemical potential of component number 1 should be the same as chemical potential of component number 1 is phase number 1. This is component number. And this is phase number, right? So we have a few equations. We could write the same thing for component number 2. Mu2 in phase number 1, Pt is equal to mu2 in phase number 2 at that pressure and temperature is equal to dot, 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 mu2 in phase number capital P at that pressure and temperature. And finally, this we can write down for the Cth component as well. Phase number 1, pressure and temperature. We are talking about component C. So now we are not going to have 2, we will have C. Phase number 2, pressure and temperature. Phase number, component C, phase number P, pressure and temperature. So we have a bunch of constraints and we need to count how many constraints do we have. So again, how many rows did we have over here? C rows, right? Row number 1, row number 2, row number C. And each row has how many equations? Equation 1, equation 2, equation P minus 1. So the number of constraints we have P rows, and each row, sorry, I messed it up. It's C rows, just confusing. So C rows corresponding to the number of components and P minus 1 equations in each. Therefore, number of constraints is equal to C into P minus 1. Therefore, degree of freedom can now be written by taking what we had over here, PC minus P plus 2, and subtracting the number of degrees of freedom. Minus,
scroll down.
yeah, I'm going to go through this again. Don't worry, I will go through this from the very beginning. I have the final equation. Let me just write this here. And as you see, this becomes C minus P plus 2. So we got the writing. Let's go over it again. This is a slightly convoluted argument. Let's go through it carefully. From the very beginning, we are trying to show that the number of degrees of freedom, F is equal to C minus P plus 2, where C is the number of components, P is the number of degrees of freedom. How do we do this? So in order to do this, we have to account for two things. We have to account for the independent number of intensive variables the system has. For a one component system, this would have been only pressure and temperature, right? So that's where we started with. This time life is complicated because every phase itself is made up of many different components. Phase number 1 is, in any given phase, phase I, you have components x1i, x2i, xci. These can also be varied at the same time. So if you have 5 different, let's say you have a 2-component system in 2 phases. What would this have meant? This would have meant x1, component number 1 in phase number 1, component number 2 in phase number 1, right? And these two should be adding up to 1. Similarly, you would have component number 1 in phase number 2 plus component number 2 in phase number 2 is equal to 1. So in addition to pressure and temperature, you have 4 more variables here that you could vary. And these are all intensive. The thing to keep in mind is that mole fractions are intensive variables. So if mole fraction is an intensive variable, it looks like you have 4 different things you can vary at the same time. So in this example that I wrote over here, P is equal to 2, C is equal to 2. So you would have had 2 multiplied by 2 equal to 4. But that's not the case because you have 2 constraints on the number of mole fractions, right? If you had P phases, then you would have P constraints. If you had 3 phases, you would have 3 constraints, so on and so forth. So you have 2 constraints. So therefore, it won't be 2 multiplied by 2. It will be 2 multiplied by 2 minus 1. Every component multiplied by the number of phases minus 1. Sorry, every phase multiplied by the number of components minus 1. It gets confusing. So that's why I did P multiplied by C minus 1. It's not P multiplied by C, but P multiplied by C minus 1. So that's our first point of writing down the number of degrees of freedom. This is only using mole fractions. So if you add pressure and temperature to it, you get P multiplied by C minus 1 plus 2, which amounts to F is equal to PC minus P plus 2. This is not what we set out to prove. What we set out to prove was F is equal to C minus P plus 2. And clearly PC is more than P. So we overcounted, we forgot for some constraints. Those constraints are the constraints of equilibrium. At equilibrium, the chemical potential, so I will write down this statement, which I used to do the math over there more carefully. At equilibrium, the chemical potential for any component should be the same in every phase. So chemical potential, and what is the notation that we are using here? We are using the subscript as the component number. So chemical potential of component number 1 should be the same in some phase alpha. And let's not use alpha, it will only complicate things more. In phase equal to 1, it should be the same as chemical potential of component 1 in phase equal to 2, chemical potential of component number 1 in phase equal to 3, dot, 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 chemical potential of component 1 in phase equal to P. In addition, the chemical potential is defined as a function of pressure and temperature, so we write down PT. We write down PT in all of this. Are these all at the same temperature and P, or at a given pressure and temperature? That's the thing. They could happen at any pressure and temperature, but now you are specifying constraints on the pressure and temperature. This is at a given pressure and temperature, which could in turn be varied. But anytime you write down, you are saying at this pressure and at this temperature. So what did we get for component 1? How many equations did we get over here? This first one is equation number 1 that connects 1 to 2. The second one that connects 2 to 3 is equation number 2. 3 to 4 is equation number 3. Therefore, P minus 1 to P is equation number P. Is equation number P minus 1. We have P minus 1 equations, right? For component 2, we have again P minus 1 equations, and every equation is a constraint on the pressure and temperature. To answer your question, Elizabeth, this is really you are specifying a limitation on the pressure and temperature. It could have varied in the domain anywhere, but now you're saying, hold on, you can't do all the possible changes. Component number C, we have again P minus 1 equations. So number of constraints that we just came up with is C multiplied by P minus 1. And all those equations were written down here. That's what I did over here. So we just derived C multiplied by P minus 1 constraints, and we had degrees of freedom. By ignoring these constraints, they were PC minus P plus 2. Therefore, true F is equal to what we first derived, PC minus P plus 2, minus these additional constraints that we just calculated, minus C, P minus 1. And now you see this is PC minus P plus 2 minus PC plus C is equal to C minus P plus 2. And we get our Gibbs phase rule in full derivation. So that's why we went through the one component example first, because as you can see, the general case is a bit complicated. It's not that confusing. It looks mathematically, it's a general case. So mathematically, it's in a tight, kind of elegant form, but it also means it's a relatively abstract way of writing things down. But physically, what did we do here? Physically, the big picture is to count the number of intensive variables. What are the possible intensive variables? Pressure, temperature, and mole fractions, right? If it was a one component system, mole fraction completely goes out the door. The only intensive variables are 2. And yeah, that's exactly what I'm doing. So if it was just pressure and temperature, I'm responding to Elizabeth's question. So if it was just pressure and temperature, the number of intensive variables would have been 2. But now you have different components, right? You have component number 1, you have this one is component number 1, this one is component number, let me write down also in more detail on a third page since it's confusing you all. So first we have intensive variables, pressure and temperature, right? Now we have C components in capital P phases. How many mole fractions does it mean in order to describe the system? That is the question. For phase 1, phase number 1, you need mole fractions for component 1, C is equal to 1. In phase number 1, you need component C is equal to 2. In phase number 1, you need component C is equal to 3. In phase number 1, right? You go component C is equal to C in phase number 1. Similarly, phase number 2, you have component C is equal to 1 in phase equal to 2, component C is equal to 2 in phase equal to 2, and C is equal to C in phase equal to 2, right? And you can write this down for different phases until you go to phase number P, where you will have component C is equal to 1 in phase P equal to P, C is equal to 2 in phase P equal to P, C is equal to C in phase P equal to P. So if I just took this into account, then how many intensive variables would I have in addition to P and T? I would have P number of rows and C number of columns, right? Row number 1, row number 2, row number 3, row number P. And in addition, I have column number 1, column number 2, column number 3, column number C. So it would appear I have P multiplied by C, number of degrees of freedom, and pressure and temperature. But now I have to take into account that in any given phase, these must individually sum up to 1. That's the nice thing about mole fractions, right? They sum up to 1. You cannot vary the mole fractions of a C component system independently. They all must sum up to 1. You cannot have mole fractions that look like half 1 by 3. Half plus 1 by 3 is not equal to 1. That's why you don't have P multiplied by C, but you have P multiplied by C minus 1. In addition, you add pressure and temperature. So you get P multiplied by C minus 1 plus 2. So that's your degree of freedom. From this, you have to subtract the additional constraints coming from chemical potential, which we got C multiplied by P minus 1. And that's how you get this. Okay. Is it still not clear? I'm sure this is still confusing to at least a few people, because that's the nature of these things. It's just confusing. I don't blame you at all. But go through the notes again, go through the video. I've worked through it now 3 times. Go through it, work through it, it will become clear. It's not profound. It's easier than the things you all have mastered already. That I can promise you. It's easier than the things you have done. It's not that complicated. And I think Atkins talks about it. If you have difficulty in finding it in Atkins, let me know. But Atkins also won't go into this much detail. So, but between this and Atkins, you can totally master it. And again, start with the one component example. Let's see what's going on over there. Then come to this one, okay? Do I have your permission to move on? Now people are still like, oh, this is so horrible. I'm gonna assume I have permission. Now we are going to talk about something fun. Now I'm going to show you all you knew about ice skating was lie. That's what we are going to show today. In fact, the common perception of ice skating is that it is localized melting. I think not let's say all. You probably know how to ice skate, probably way better than I am. I'm terrible at ice skating. But that's because I grew up in India. There was no ice, right? It's like for 3 months, it would be about 100 Fahrenheit in the summer. It's really hot. So what I will show you is that the localized melting picture of ice skating is completely wrong. In fact, it would require an elephant to be in a ballerina shoes for ice skating to work through localized melting. It's something else. We won't go into how it works, but I will show you it's not localized melting. In order to do that, we have to look at something slightly more abstract. What we have to do is to learn how to characterize, and this goes back to, I think, Jared's question from early on about the phase boundary, what happened to the pressure and this and that, how to characterize phase transitions. And I will be doing it in a very general setting, and it's quite nice and it's not complicated. It's easier than the proof of Gibbs phase rule. So I have my pressure, temperature phase diagram. And let's say I have some curve, some phase boundary between phase alpha and between phase beta. So this is my phase boundary. And the question I'm asking is, I just drew a curve. What can I say about this curve? Can I say anything about the equation governing this curve? Does thermodynamics tell me to talk about the equation governing this curve? If it could, it would be super cool, and you will see why. I mean, already I think it's quite cool that you can use principles of thermodynamics to write down a mathematical equation about how exactly, this curve here, what is this curve showing us? This curve is telling us that in order to go from beta to alpha, if you do it at a temperature T is equal to T1, the transition will happen at a certain pressure. Let's call it TA. At a T is equal to TA, the transition happens at a certain pressure PA. But if you go to a temperature T is equal to TB, the transition happens at a certain pressure PB. And it is telling you how much does this pressure for the phase transition, not for the phase transition, how much does the pressure for the coexistence of alpha and beta change with temperature. You can reverse it and you can think about it, ice, right? This is ice. If this is ice and water coexisting at point A, could be the sea level, or well, it's low pressure. So let's say point B is sea level, and point A corresponds to the top of Mount Everest. When you go up to the top of Mount Everest, the pressure goes down, right? So if this thing applied to ice, this would mean that at top of Mount Everest, as you decreased pressure, ice would melt at an even lower temperature. It would become, this is actually not true. For water, this curve tends to look opposite, and we will get to that. So we are really trying to describe something quite physical. What is the temperature at which phase transitions happen as the pressure is varied, or what is the fresh pressure at which phase transitions happen as the temperature is varied? So we want to characterize this curve. So let's work in the differential limit. Let's say that, I will use a different color over here. Let's say that this temperature variation is dt, and let's say that this pressure variation is dp. So I want to talk about dp by dt. I want to calculate what is dp by dt as a function of pressure and temperature. It is the slope, and I want to calculate the slope as a function of pressure and temperature. Why? Because that's super useful. If I know the slope as a function of pressure and temperature, I can integrate P is equal to integral dP by dt and get my pressure at any other temperature, right? If I knew the slope. So it could be quite useful. So how do we do this? In order to do this, let's imagine that phases alpha and beta are in equilibrium. Well, that's what I told you, so it's not hard to imagine. Both at point A, so this over here is my point A, and this over here is my point B, are both at equilibrium with, both at, I already wrote equilibrium, points A and B. Because that's the phase boundary, right? They are at equilibrium at this point also. They are at equilibrium at this point also. I'm just picking up two of them, points A and point B. What would this mean? This would mean that the chemical potential of phase alpha should be the same as chemical potential of phase beta at the pressure at point A, PA, as well as point B, PB, TB. Notice here that unlike last time, unlike few minutes ago when we were deriving Gibbs-Duhem equation, we were having to tag along this subscript, mu1 and mu2 and things like that. We don't have to do that right now because we are thinking about a one-component system, okay? Life in multi-component systems is complicated. If you really get frustrated by the second proof of the Gibbs phase rule, by the general proof, I will not like you any less. It's complicated. Components are complicated. Although I would be very sad if you don't really get to grips with the first proof of the Gibbs phase rule just for a one component system. That should be very clear to you. If the multi-component stuff is not very clear, it's okay. Please try, it should become clear, but the one component stuff should be clear. In general, after this, next week next week and beyond, we'll be talking about solutions, and you will see multi-components are funky, they are complicated. But now we are just talking about one component system. So we can say that the chemical potential for phase alpha should be the same as chemical potential for phase beta at point A and at point B. What does this mean? If we just write it down, this one over here as mu alpha at point A is equal to mu beta at point A, and write this second one as mu alpha at point B is equal to mu beta at point B, we can think we have just done a slight change, right? We have not changed our system. In going from A to B, we have caused a very tiny amount of change in temperature and pressure. So let's try to think about this second one as some change in the chemical potential of phase alpha relative to point A, and some change in the chemical potential of phase beta also relative to point A, right? So since my temperature and pressure changed by a very tiny amount, a differential amount, dt and dp, I'm saying that, let's say this changed mu alpha and mu beta by d mu alpha and d mu beta. That's the idea over here. So let's number our equations. This one was equation 1. This one was equation 2. And equation 2 can be written as equation 3. It's a small change, right? If now I compare 1 with 2, 1 with 3, what do I get? So I'm comparing, I'm using 1 in 3. One tells me that mu alpha in A is equal to mu beta in A. So this, why am I erasing instead of writing? 1 tells me that this thing is the same as this thing, right? That's just written over here. Mu alpha A is equal to mu beta A because they were in equilibrium at the initial point. We get d mu alpha is equal to d mu beta. It looks like I derived it mathematically, but I wrote down something very simple. And what I did here was to say that if the chemical potential of two phases, alpha and beta, are the same at point A, and if you make a tiny change and go to a point B, and they are also still in chemical equilibrium, then their chemical potentials for the two phases must have changed by the same amount, right? Chemical potential is like, I am at the same level of gravity as you, then I do some change to me, and then I do some change to you, and we are still at the same level of gravity. Then the amount of heights we must have changed must be the same. There is no other way that we are still at the same level of gravity. So d mu alpha is equal to d mu beta. But now we know that dg, let's actually go to next page before writing this more. So we just showed, to recapitulate that curve for you, we have a pressure temperature curve. We went from point A to point B, where this thing was dt, this thing was dp, and I just showed that, and this phase was alpha and this phase was beta, and we are trying to characterize the curve in between them. So I just wrote down that d mu alpha is equal to d mu beta, where d mu alpha, and so there is no longer any A or B over here because I'm just talking about a differential change at a given point. However, mu is G per mole in a one component system. right? If it was multi-component, again, life would be very complicated. In a one component system, mu is simply G per mole. And dG is equal to V dP minus S dt. We know this. This is our integrated first and second law of thermodynamics. Therefore, this equation 4 that we derived, equation number 4, can be rewritten as dg alpha is equal to dg beta. Again, it's a one component system. It was not one component. It can still be done. It will be a bit more complicated. And we use this thing for dg over here. What does that mean? That means that V alpha multiplied by dP minus entropy of alpha multiplied by dt is equal to V beta multiplied by dP minus entropy beta multiplied by dt. Or we can bring both the dt's on the left side, S beta minus S alpha multiplied by dt is equal to V beta minus V alpha multiplied by dP, or dP by dt is equal to V beta minus V alpha by S beta minus S alpha. And that's fantastic. This is the change in volume during the phase transition, and this is the change in entropy during the phase transition. What we have just derived is a beautiful equation that tells us that the phase boundary follows this equation. And this is absolutely general for a one component system. We have not assumed anything. This is the equation governing the nature of the phase boundary. Delta V transition, how much does the volume change, divided by delta S transition, how much does the entropy change. Did I screw up something? I think I did. dP by dt, I did it opposite in my enthusiasm. I flipped the order, very sorry about that. dP by dt is equal to S beta minus S alpha by V beta minus V alpha is equal to delta S transition by delta V transition. This equation is super important. It has a name. It is called the Clapeyron equation. Next lecture, you will see the Clausius-Clapeyron equation, which is a specific case of the Clapeyron equation. But this one has, it is about equilibrium. It does assume equilibrium. It is about coexistence. So that is equilibrium. Coexistence is equilibrium. However, it did not assume ideal gas, things like that, right? At no point did we assume PV is equal to nRT or anything like that. It is super general. So now, before I go into ice skating, because I won't have time to tell you about ice skating, but I would like you to think about it and see why you might see from this that ice skating is not going to work. But I want to show you something about the phase boundary of water. This already can tell us something about the, let's draw two possible phase diagrams for water, for solid and liquid. And we can already rule out one of them simply on the basis of this equation. And that I think is quite interesting. Option 1, or option 2. Let's go to the next page and work on it in detail. So how do we do that? So for water, we have pressure and temperature, we have solid and liquid. This is option A, and the option B is solid and liquid. Which one is correct? How do we do that? Let's look at our dP by dt is equal to delta S by delta V. So we are talking about S, and we have to be careful in our sign convention. Let's say that we are talking about S liquid minus S ice by V liquid minus V ice. S liquid is more than S ice for, or rather let's write it down as solid, and then we can write down the general case. I will do this again next time. So if I feel like I'm being rushed, don't worry, I will go to this. Next time I'm going to start from Clapeyron equation from this point, dP by dt equal to delta S by delta V, and go through the ice and water example again in detail. But let's do it once for now, just for kicks. So we know that the entropy of liquid is going to be more than entropy of solid for any material. That there might be some counter examples, but it's almost very common. For water, it's definitely true that the entropy of liquid is more than entropy of solid, right? We saw. How did we know that? We know that ds is equal to dq reversible by t, and and that's the integral. Cp is positive, so that's how we get this. However, V liquid and V solid is true for almost any material except water. That's where the water is very, very funky. Ice floats on top of water. You have seen this, right? If you go camping in a really cold time and you have a bottle of water, and you really want, you have those Nalgene bottles, and sometimes you must have experienced it at some point. And next morning you cannot open your Nalgene bottle because the ice, when it forms, it goes to the top of the Nalgene bottle. It always floats on the top, and you're unable to open it. So if you want to go snow camping, one of the first tricks is to always keep, this is my coffee cup, so I cannot invert it, but the first trick is to keep your bottle inverted, so that the ice, when it forms at the bottom of the bottle, not at the top of the bottle. So for ice, V solid is actually more than V liquid. The density of ice is lower than the density of water. Therefore, dP by dt is negative for water. Almost any other material will have a solid liquid curve that looks like this, but for water, the solid liquid curve will have a negative slope. And I say everything else, but it is really almost everything else. I think helium-3, superfluid helium, very close to 0 Kelvin, also has funny behavior. That's, however, not due to the volume. Superfluid helium has an issue in this curve due to the entropy. Superfluid helium is one of those materials where it's another story, and I don't think we can talk about it in this class. It's something very, very funky happens, and the entropy displays non-trivial behavior. So hopefully this is clear to you now, that using this Clapeyron equation, we can see why the phase boundary for water has a negative curvature, and for everything else, it's a positive curvature. So I did this. Next time I'm going to start over again from Clapeyron equation, and we will revisit this example and also look at ice skating. So Tuesday, there will be office hours. There is a homework due on Wednesday. I won't be doing office hours on Monday. I will be there to answer questions on Slack and everywhere else. I will be doing my office hours the following Monday, but not this Monday. Unfortunately, I have a day-long meeting right after the class, which I cannot seem to get out of. If anyone needs some urgent consultation of any sort, we can arrange an interview. Why is liquid on top of the water and solid on the bottom compared to everything else? It's all about the curvature. When you go from solid to liquid, when you go, it's not top bottom, it's a question of curvature. Don't think of it as top and bottom, think of it as left and right. Solid is to the left, liquid is to the right. That is what we are really showing here, right? So solid is to the left. I'm putting my hand on the iPad as if you can see. Solid is to the left and liquid is to the right. In this one also, solid is to the left, liquid is to the right. It just so happens that the curve in between them, for everything else, dP by dt is positive, but for water, dP by dt is negative. That's why. To answer your question, that's Clapeyron equation, which is telling us that the liquid is on top of water and solid is on bottom. Okay, we will do this again next time. We will look at solid liquid, liquid water, and water gas transitions for general materials, and we will move from there. Okay, so see you on Monday.